Do a few example problems illustrating how we might want to try to solve various antiderivatives or definite integrals or find an antiderivative or see what they're equivalent to or any of these things, right? So what do I mean? We want to see which one is equivalent to this definite integral. It's from 0 to 5. And actually, thinking about it, you could actually cheat and you could actually use your calculator and see which of these gives you the same value. In which case, those would be your answer, but they want us to do it a slightly different way. Oh, they probably don't allow the calculator for this one, so there you go. Okay, now let's see. So the first one, right? The first one's essentially saying that the integral of the numerator divided by the integral of the denominator is equal to the integral of the division of the two functions, which is not a rule. So one immediately I'm going to cross out as being not true. Okay, you cannot split an integral or an antiderivative. The integral of f of g, the integral of f of x divided by g of x does not equal the integral of f of x dx divided by the integral of g of x dx. That is not a rule. Do not try and memorize it. None of that. That is nonsense. Okay, and I'm purposely erasing it to illustrate that that is not true in general. Okay, now the next one. Okay, now this one. We gotta kind of do something here. Okay, so how do I investigate whether this one's true? Well, the question would be, how do I evaluate this integral to begin with? Right? I look at this integral, and what I see is that the degree of the denominator is not strictly greater than the degree of the numerator. And when that's the case, that tells me that I could divide. So I'm going to divide. So I'm going to just do some algebra here, right? I'm going to change this inner rational function by actually doing that division. So I'm going to get x plus 2 here, and then 3x plus 11. And I divide. X into 3x goes in 3 times. I distribute the 3x plus 6. I minus the whole thing. This is 0. 11 minus 6 is 5. 5 is of a lower power than x to the first, so that is my remainder, plus 5 over the divisor, x plus 2. And I just did the division of the two polynomials, since this is indeed a rational function. Now, this is just the same thing as this, right? It's algebraically the same thing. These two here are algebraically equivalent. So, of course, the integral from 0 to 5 of 3 plus 5 over x plus 2 dx is the same as this original one. So definitely 2. Now we want to investigate 3, and that's tricky. Okay, 3, we need to see how we could deal with perhaps a u substitution. So again, I start with 0 to 5, and there's another way of doing this integral essentially. And you'll get the same thing in both cases. Now, what's tricky about this is that these bounds, 0 and 5, those are the bounds of my definite integral, they're going to change when I change from x to u. So I let u equal, let's say, x plus 2. That means that du is just going to be equal to 1, right? And the derivative of 2 is 0 dx. So this is just a simple substitution now. But the thing is that I'm not going to write these bounds in, because remember, I said that they're in terms of x. And I'm changing now to u. So the first thing that I'm going to do is I'm going to write it as, instead of, right, in this one, and this is tricky, we've yet to do this, I have u is equal to x plus 2. But that immediately implies something else. That immediately implies u minus 2 is equal to x. So that means that in this x here, I could write 3 times u minus 2 plus 11 over, instead of writing x plus 2, I can write u and then du here, because instead of writing dx, I write du. So I'll write it again to make sure that it's clear. So I'm going to leave the bounds out for the time being. X, I made u equal to x plus 2. So I minus 2 on both sides in order to solve for x. And I get x equals u minus 2. So instead of writing x here, I write u minus 2. So I get 3 times u minus 2 plus 11 over u du. Now I'm going to distribute the 3. 3u minus 6 plus 11 over u du, which is then just 3u plus 5 over u. And now I use a fact from algebra that I could split it along the numerator, right? So it's going to be, this is going to be the same thing as 3u over u plus 5 over u. I split it up along the numerator. And this cancels. And when I do that, I can see that this is just 3 plus 5 over u. But now what about those bounds? Okay, well, the bounds are simple. Just know that this is an x bound, this is an x bound, right? But now you're integrating with respect to u, du. So you just use the relation between x and u to get the new bounds. So u, the lower bound, right? Well, the lower bound for x was 0, so it's 0 plus 2. So that lower bound becomes 0 plus 2, which is just 2. The upper bound was originally x was 5, right? The upper bound, so then it's just 5 plus 2, which is 7. And that's the upper bound when we're integrating with respect to u. And it is true that this now, right, because this is just 3 plus 5 over u du, and then the bounds have changed appropriately, right? So it's definitely 2 and 3 as your choice D, okay? Now, doing this is the whole point. The whole point is that there's more than one way to evaluate this integral. I could have used this here. Once I got this, I could have found out what this definite integral was now at this point, because I know the integral of 3, and I know that this is 5, 1 over u. The antiderivative of 1 over u is ln of u. And then I plug in the upper bound minus the lower bound, and I get my value. Similar idea here. With this one, I know that it's going to be 3x plus, right? The 5 comes out. The antiderivative of 1 over x plus 2 is ln x plus 2. And in this case, I'm plugging in from 5 to 0. And I'd plug in 5, and then I'd plug in 0, and I get the same thing that I had over here. I guarantee it. You'll get the same value. Both of these definite integrals will be equal. Now, in this case, right, so how do I do this now? Let's look at this one. So now it's asking us which are equivalent in this case, right? Or it's only asking for one. So this is much easier. When they give us these multiple options, such a pain. Like, I don't know, maybe, well, 1, no, we know for sure, not only 1, but then B, C, and D are all sort of like, well, I don't know, we got to do some analysis, we got to see. I convince myself of, if you convince yourself of 2, right, what do you have? Do you have anything? 2 only? No, then you know that this one then is wrong. If you convince yourself of the other one, so it'll be a 50-50 shot. If you can convince yourself of one of them being true, but not the other one, you're not sure, then you got a 50-50 shot, right? So, if you can convince yourself of both being true, then you have a 100% shot. But all right, whatever, the analysis. Okay. This one's easier because there's less of a probability involved. But here, let's see. So I got 1 to 2, and all you do here is you use the rule that you could split it up along the numerator, and that's it. So I'm just splitting up every piece along the numerator. X to the 7th over x squared minus 4x to the 3rd over x squared plus 6 over x squared dx. And then you just do this division for each one. This is x to the 5th minus 4x plus 6 over x squared dx from 1 to 2. Which one says this? X to the 5th minus 4x, your answer is C. That one, simple, right? That one we just got to see. the degree of the denominator is greater. You could do this is called short division. The long division is what we did in the other one, right? This is called short division, where we just break it up along the numerator. This one, right, where I did that division, where did I do it? Over here, right, I did this division, right? This is the long division right here. When I did the 3x plus 11, and then I did x plus 2, right? 3x plus 11 divided by x plus 2, and I got this here on the top. That's called long division. The short division is just when you just kind of break it up along the numerator, right? These all have the same numerator, so you can combine them into one numerator, x squared, and then you add these all have the same denominator as x squared, so you can combine that denominator as being x squared, and then you just add the numerators, x to the 7th, and you get back the original one, right? That's the way to go backwards. Seeing it backwards is a little bit easier. And then you could integrate this, and that's the whole point. Well, how would we integrate this? Well, that would be easy to integrate as well, because that's just x to the negative 2, and then you just use that power rule. Okay, so we'd be okay. We'd be able to find this integral, this definite integral. Okay, similar idea, just using the algebra. Okay, so let's see what we got here. So similar idea again. What we do here is we just have it where what we want to do is we just do this algebra process. I'm going to distribute this square root x into each of these terms, and then what I get is going to be my result. That's it. Which one of these is equivalent? That's all it is. So this is 3 plus a half, right? Because when I distribute that, I'm going to get 9x cubed times the square root of x minus the square root of x times the square root of x is just x plus 8 over the square root of x. So I did some algebra real quick there, right? The square root of x divided by x is just a square root x left on the bottom. This is then, in turn, let's see what it'll become. So this is really x to the 1/2, right? 9 x to the third times x to the 1/2, but this is 6 halves and 1/2, right? The exponents add 9 x to the 7 halves. Not going to bother writing it again, minus 2 plus, and if you like, 8x to the negative 1/2 dx. And if you left it like this, you should be able to recognize that as x to the negative half, that 1 over x to the half, right? And then you bring it up and it becomes negative. Now, which one says this here? And it's B, right? And we're done with that one. And again, it's just algebraically manipulating the inside of that integral there. Now this one, we go back to something like this, and we see we have to do some work here. Okay, so just like in the other one, you want to first divide. You want to try and do that division. So you got from 2 to 4 in this case, 2x plus 5 over, and I'm going to write it negative x plus 5 on purpose because I'm used to going in highest to lowest power. So then now I do that division. So let's do this division. Negative x plus 5, 2x plus 5. And then what I get is I divide in, I'm going to get negative 2 here, right? And then the negative 2 times negative x is positive 2x. Negative 2 times positive 5 is negative 10. And I remember that I got to subtract that whole thing. This is going to be 0. 5 minus negative 10 is 5 plus 10, which is 15. And this is my remainder, plus 15 over negative x plus 5. And I want to see which one is equivalent to that. Well, this is 5 minus x, right? So definitely 2. And 1 we should eliminate immediately because it's that same junk rule that I told you that's not a true rule, right? The definite integral from a to b of f of x, f over g of d of x does not equal the integral of f dx over the integral of g dx, right? Does not. That's a junk rule. So we know it's not 1. So now I know it's 2, right? So I know it's not A, and then I know it's not just C, right? So I know it's got to be between B and D again. And similarly, we got to see whether 3 is true. Right now, you're at a 50-50 shot at guessing. Now let's go and do the next one here. So the next one is going to be that u sub, like what we did in the last problem. So these typical ones where you have a linear function on the top and a linear function on the bottom, they can be solved in two ways. You could divide or you could do a u sub. And this is what we're going to do in this case. We're going to do a u sub. So now a u sub, right? U equals, and make u the bottom part. So 5 minus x. This means that du is just negative x. Now, after you have that, right, you kind of maybe want to solve for x, okay? So solving for x, if I minus 5, I'd get u minus 5 equals negative x. That means that x is 5 minus u. And now I'm good to sort of plug in here, right? So I'm going to leave the bounds alone, or maybe I'll switch the bounds now. It's fine, right? These are x bounds. I'm integrating with respect to x, and I want to change that to u. So I just put in the lower bound into this relationship between x and u. So the lower bound then is going to be, well, the lower bound originally for x is 2. So then the new bound within terms to u is going to be 5 minus 2, which is 3. And then 4 for the upper bound is, it's originally x, right? It's originally, the upper bound for x is 4. So I plug that in to get the upper bound for u, which is 1. And then now I substitute everything in. So I get 2 times, instead of writing x, I write 5 minus u plus 5 over, the whole thing is u, and then instead of this I'm going to put negative du, because I know negative du is equal to dx. Now these bounds are in reverse order. I have the lower bound being higher, so I'm going to flip them and make the integral negative, right? So it starts off as negative, so when I flip it, it just goes back, this minus goes away, right? The negative of a negative is now positive. I get 10 minus 2u plus 5 over u du. And then this 10 and 5 combined to being 15. I could write this as, when I do the splitting along the numerator, right, we should see that it's really just 15 over u minus 2. And I just continued with this algebra process, right? I did 10 and 5 is 15 minus 2u, and then I did the 15, oh boy, the 15 I did the 15, apologize, minus 2u over u as 15 over u minus 2u over u, and then I canceled out these u's and I got this here, and that is exactly what number 3 says, if I'm not mistaken. It is. So we know that the choice is D. And you're done with these 4. So again, you see something like these ones are by far the trickier type, right? The first one and the last one are by far the trickier type. These are just sort of just manipulating them algebraically with more basic rules of algebra. Just got to be careful with the bookkeeping.